Hello everyone, welcome back for part 3 of chapter 30. And the ongoing theme for this chapter is that any change in magnetic flux can produce an induced EMF within the coil or the loop in our circuit that we're considering. And that induced EMF can then produce an induced current within the conducting material. And then that induced current can produce an induced magnetic field by way of the right-hand rule. And that induced magnetic field can then cause a counter effect to whatever the initial cause of the change in magnetic flux for the system is. So keep in mind the magnetic flux is the combination of magnetic field, cross-sectional area, and angle relationship between the two vectors. And so if any of those three values changes, we get a resulting electromagnetic force, so induced EMF, that relates to an induced current within the material, which in turn can produce an induced magnetic field, which is then going to try to counter whatever it is that initially caused the magnetic flux in the system to change. And this counter effect has to happen, otherwise the only alternative to countering the effect is to compound the effect. And we cannot have a changing magnetic flux generate an induced EMF that will cause an induced current that will create an induced magnetic field that will continue to strengthen the change of the original magnetic flux in the system. So if that were to happen, we would have a constantly increasing magnetic flux, and it would just end up as this chain reaction to infinity, which, as we know, is not going to happen. The universe has this thing called entropy, which does not really allow for high concentrations of things. Instead, entropy is more about disorder, spreading things out and producing lower concentrations. And so that's where that countering effect has to come in. So in the last video, we saw the methods in which we changed the magnitude of the magnetic field. And then we saw an example where we changed the cross-sectional area of our circuit or loop or coil, whatever term you want to use for it. And so now we need to see what happens when we change the angle that exists between those two vectors, A and B. And to do this, we're going to make ourselves a rectangular cross-section of wire. And I'm trying to draw this in a 3D fashion here. That didn't exactly come out as good as I'd hoped. Try that again. Oh, that's a little bit better. So we have this rectangular loop. We can put in dimensions if we need to. We could say that the side leg here is length A. The side leg down here can be length B. And then what I have up here with this portion of the wire is basically just a means in which I can allow current to either flow one direction or another within that loop. And I also want those two extending portions of wire there, because what we're ultimately going to do is we're going to allow this loop of wire to rotate. And that is what will allow us to change the angle relationship between our cross-sectional area vector and our magnetic field vector. The next thing we need to do is we need to define what each of those vectors looks like in the problem. So I am going to place one end of a very large magnet on one side of this coil, and I will place the opposite pole of another very large magnet on the other side. And what this is going to do is it will provide us with a nice uniform area of magnetic field through which our coil can rotate. And at any given moment, the coil has a cross-sectional area, and there's a vector that relates to that cross-sectional area. And that area vector will point perpendicular to the surface of that coil. As our coil rotates, then we can see that the angle relationship between our magnetic field vector and our area vector changes with respect to time. Any kind of change that we see in any kind of system can be measured as a changing rate with respect to time if we want to set it up that way. So that's what we have here. We're going to keep the dimensions of the loop fixed so that the cross-sectional area remains constant. So this is a constant value. We will leave the magnets alone, and so whatever magnetic field magnitude exists, that will also be constant. And so the only thing that's changing is theta. So that means that when we go to look at the change in our magnetic flux, the only thing that's changing is our theta term. And the next thing that we have to do, so that we can figure out what the induced EMF in this system is going to be, is we need to take the derivative of the flux expression. The negative n out front, the negative is there to remind us that whatever happens in the system, the electromagnetic induction is going to counter that effect. The n is there to measure the number of loops that exist within our coil. This n over here, that's just the north pole of that specific magnet. That's the south end of that magnet. So not the same n values, obviously. But since we only have the one loop in this case, if we need to, we can just say that n is equal to 1. But in some other problem, you may want to put multiple loops in that coil. So keep that in mind. Now, the derivative that we need to take is the derivative of our magnetic flux expression. And as we said, both B and A are going to remain constant. Theta is the only thing that's going to change with respect to time. So we now have negative n BA, derivative of cosine theta with respect to t becomes, derivative of cosine is negative sine theta d theta dt. The negative sign will come out front and it will cancel with the negative sign that we already have. So now we have NBA sine theta d theta dt. So what does this mean for us? Well, the number of turns, magnetic field, and cross-sectional area vectors, those are all fixed. Sine theta will have to be evaluated at some instantaneous value for theta. As our coil rotates through this magnetic field, there will always be some measurable instantaneous value for theta that exists between the two vectors. But at the same time, there is also a rate in which that angle is changing with respect to time. So what we're going to do is we're going to take that changing rate and we're going to modify it such that we can basically combine both of these terms into a single term. And if we think back to our days in Physics 1, whenever we had something that was rotating or spinning in a circle, there was a certain angular displacement that we would pass through. And if we measured that angular displacement with respect to time, then we could call that combination the angular velocity. And so this coil is going to be spinning at some rate of angle per second. That angle needs to be measured in radians. All of that angular motion stuff back from Physics 1 had to be measured in radians. And so what we can do at this point is we can say that by substituting in for sine theta and d theta dt, well, d theta dt, this is just the instantaneous version of this expression. In fact, the delta statement, the best that we would be able to do with that would be an average angular velocity. But in the case of d theta dt, this would be the instantaneous angular velocity for that system. So we can replace d theta dt with omega. But then theta, it would not be all that easy for us to measure the instantaneous value of theta at any given time as this coil is spinning, especially if it's spinning at a fairly fast pace. So instead, what we could do is we can go back to this expression right here, and if the angular velocity is constant, if we're spinning this coil at a constant rate, then we can say that the angular position is equal to the angular velocity times time. Remember, our angular velocity has units of radians per second, and if we multiply that by the time, or some specific time during the rotation of this coil, then what we get is a theta value. And so we're going to replace theta in that sine term with sine omega t. And this is to our benefit because now our expression for the induced EMF in this coil is a time-dependent function. Okay, it's dependent on time. Now, if you're not quite sure about these substitutions that I just made, that's okay. Let's come back up to this line in our derivation, And let's make the substitution of omega t right here. So if we do that, if I replace cosine theta with omega t, let's see here, we have negative NBA. Whoops. Negative NBA. We need the derivative with respect to time of cosine omega t. We still have the negative NBA out front. The derivative of cosine still turns into negative sine. We have sine of the parenthesis set. But now we have to follow through with the chain rule. So we start on the outside and we work our way in with the derivative. And so the next step in the chain rule is to take the derivative of what's inside the parenthesis. And if we do that, the derivative of omega t is omega. Well, so what does that make? That makes 2 negatives is a positive. There's NBA. We've got an omega. And we have a sine omega t. So it's the same expression that we got in both cases. And in both cases, we have this time-dependent function for our EMF. Well, think back to your days in trig and plotting out sine functions and cosine functions. In the case of a sine wave, your sine function continuously alternates between positive and negative 1. And that happens with respect to pi over 2, pi, 3 pi over 2, 2 pi, and then it just keeps continuing with that pattern as we continue on. And so this portion of the function will constantly just alternate between values of plus and minus 1. Everything else out front is what we would categorize as the amplitude of this wave function. And so by multiplying 1 by the product of NBA omega, our wave function will now alternate between the values of positive NBAW and negative NBAW. If our induced EMF function is alternating back and forth between two fixed values, then what is going to happen to the induced current within this system? My coil has fixed dimensions. There's a certain amount of material associated with this coil. So the coil has some resistivity value associated with it. Maybe it's made of copper. The length of the wire that's used to make that coil, the thickness of the wire itself. So these are both values of the wire. Those are what dictate the resistance of that coil. As such, the induced current within this coil is only going to differ from the induced EMF by the scalar value of R. So we now have NBA omega R sine omega t. Got my parenthesis in the wrong spot there. So again, the sine omega t will alternate between plus and minus 1. and everything else becomes the amplitude of the current that we see. This is what we define as an alternating current. And it's kind of self-explanatory now because we can see that the current is alternating back and forth between two maximum values. And where those maximums and minimums occur can be found by taking the derivative of this current function and setting it equal to 0. Because the derivative of a function is supposed to measure the slope of that function at any given location. And whenever we're at a max or a min, the slope is going to equal 0. So we can find out exactly where the maximum and minimum values need to be, and then we can just average the times between the two, and we can find out when the current has to have a value of 0. Or we can just set the current equal to 0 and solve for what value needs to go there. But not every EMF or current is going to alternate at the same rate. The rate with which our EMF switches back and forth is going to be determined by the rate in which we spin that coil. We could spin that coil very slowly, and so that means that there's going to be a very wide graph for the change in the EMF, also a very wide graph for the change in the current. But if we were to spin that coil very, very quickly, then we would see alternating EMF and alternating current jumping back very quickly as well. Okay, so now that we have that, now that we can see what the induced EMF is and what the induced current is, what is that induced current going to do? Well, we have induced current that is going to be running through this coil, and at this point there's really no advantage to trying to draw the direction of that induced current because it's constantly going to be switching back and forth as we rotate this coil. So what's going to happen with any induced EMF and induced magnetic field? Well, the induced magnetic field is going to have to counter whatever is happening within this system. So there's going to be an induced magnetic field that is going to point in a direction that will attempt to stop the coil from spinning. Okay, so that means that in order to prevent this coil from continuing to spin this way, we would have to have some kind of a magnetic field that would provide rotation in the opposite direction. And that means that we would have to have some magnetic forces acting on either side of this loop to try and provide that counter rotation in the system. Okay, well, if that's the case, which way does the induced magnetic field need to point? And we can find that if we pick a direction for the induced current. Keep in mind that current's going to switch back and forth, but at at one moment in time, that induced current has to have one direction associated with it. So let's say our induced current is traveling this way. With respect to the two legs, the induced current is going to be pointing in those directions. Those directions can be used as the length vectors in the cross product relationship. And from here, we can find out what direction the induced magnetic field needs to point. We need to focus on one side at a time. So if I look at this front leg of the coil, the first vector in my cross product, L, that's the index finger that's pointing down. The resulting force is pointing to the right, and that's going to be our thumb. So we need our index finger pointing down, we need our thumb pointing, to the left. I think I said right earlier. Index finger down, thumb to the left. And then the second finger in our cross product, that's our middle finger. And the only way the middle finger can currently point is out of the page or out through the cross section towards us. And then if we try the same thing with the other end, okay, L has to point up, force is thumb, that points to the right, middle finger has to point out of the page towards us. And so that would be the direction of the induced magnetic field when the current is flowing that way. But then our coil rotates to some point where the current flips around. So what's going to happen when our current flips over? Well, you can go through and flip over all of your L vectors. Oops. Come on, eraser. We can go through and flip over all of our L vectors. But keep in mind that even though the current has flipped over, the coil itself is still rotating in the original direction. And so we need to maintain the same direction of magnetic force. And that means that the induced magnetic field will have to change its direction just as the induced current did. So it's one long continuous chain as we keep track of one event affecting another, which affects another, which affects another, which then in turn goes back and affects the original event. I will admit, the first time that I went through and I was studying induction, I was really lost because we keep saying that induction has to counter what's happening in the system. And the easiest way that I can think of to keep all that information straight is imagine that you are physically the one that is responsible for doing this action right here. You are the one that has to spin that coil, and you're the one that's causing everything else to happen. Well, at the end of the day, the final effect is going to have to counter what you are doing to the system. And this is the primary reason why perpetual motion machines don't work. And that's because regardless of what you try to do, you cannot you cannot get more out of the system than what you originally put in. There's always going to be some kind of resistive force or some kind of counter effect in the system that prevents this object from continuing to remain in motion. But this is the type of approach that we use in generating electricity for our infrastructure. We use this alternating current method, and when you plug something into the outlet in the wall, you are receiving an alternating current value of approximately 120 volts. And so what this means is that the electric potential that is sitting inside the wires of your house are constantly jumping back and forth between 120 volts. So really, really, what's the true difference between the two? Because you're not just going from 0 to 120. You're going from 120 to negative 120 to positive 120. So you've actually got a difference of about 240 volts happening there. And the reason why we use this method is, first of all, it's easier, but it's also safer in terms of the energy transmission. When it comes to direct current transmission, think about all the people that live 100 miles away from the power plant. You have 100 miles worth of power lines that the electric charge has to travel through, and after traveling that far, how much current are you actually going to get after you've passed charge through hundreds and hundreds of miles worth of wire? You would have to have an incredibly high electric potential from the power plant. So I'll get a power plant over here. You would have to have an incredibly high electric potential over on this side just to get the slightest trickle of electricity out to someone's house. And so the idea of having alternating current, by alternating the charge flow within the wire, you don't necessarily have charge that's moving all the way through the wire. Instead, the charge is just kind of sloshing back and forth until it's needed and until it's used. And that potential difference then works in conjunction with things like transformers. And this is getting beyond my expertise. At this point, we're better off leaving the discussion to the electrical engineers, because I'm probably going to end up saying something that's incorrect at this point. But there was a huge battle between Thomas Edison and Nikola Tesla about what version of electricity we should be using. And Edison was a big proponent of direct current, and Tesla was a proponent of alternating current. And Edison was an inventor, capitalist. He had tens of thousands of patents. Most of them didn't work, but if you're going to invent something and you do get lucky and it's a big breakthrough, then you make lots of money. So Edison had all of these ideas, and in all honesty, the math for direct current is easier, even though it's not as efficient. And Tesla, well, he was able to get around the math with the alternating current, and he found that you could actually provide the electricity over a long distance while keeping the cost fairly low. And so it came to the point where people were going to have to decide on what method they were going to use. And so the way that they finally came to a decision was that Tesla and Edison were at the World's Fair. And I want to see if I can find the date for that particular World's Fair. Get my Google function going here. World's Fair electricity. Let's see what that gives us. Okay, this was in 1893. 1893 World's Fair. And this happened in, I think it was Chicago. And they wanted to light up the entire World's Fair area at night using this new thing called electricity. And so there was a big push to start using electricity as a lighting source because people felt it was, probably cheaper and safer than trying to use gas lamps. And so Tesla was actually able to outbid Edison when it came to putting all this together. And so they had something like, I think it was 100,000 incandescent bulbs that they set up throughout the World's Fair area. And the time came, they flipped the switch, all the lights came on, everybody was, ooh, ah. And so it was decided that AC was going to be the way to go. One of the problems with AC is that with the alternating electric potential, you have a fairly high electric potential, which is constantly jumping back and forth between the two values. And this can make for some very painful interactions if you ever get electrocuted with this stuff. And Edison was not happy about losing the bid, and he started a smear campaign against Tesla even before the World's Fair happened. And there's a story. It's a true story. It doesn't have a happy ending, however. One day the circus was in town, and as happens from time to time, one of the animals will get fed up and attack one of the handlers, and that's what happened in this case. There was an elephant that killed one of the handlers, and when that happened, the only recourse was to put the animal down. And to try and put down an elephant is not the easiest thing, apparently. There are some stories of taking elephants down to the train yard, and they would hang them from a crane. Again, not a happy story here. But they were getting ready to put down this elephant, and Edison said, "Wait a minute, let me try, let me kill it." And Edison set up this system with metal plate and an AC generator, and they walked the elephant onto the metal pads, and they flipped the switch and killed the elephant. And Edison said, "Now you see, that stuff's really dangerous. You want to put that in everybody's home." Well, Tesla's response was something like, "Well, just don't stick your finger in the outlet and you'll be fine." And here we are today, more than 100 years later, and again, the first thing that we learn is don't stick your finger in the outlet and you'll be fine. So still, Tesla was able to outbid Edison, but Tesla was very much a humanitarian. He believed that any scientific discoveries and breakthroughs should belong to mankind. So he gave all of his discoveries away for people to use. Problem was he didn't have the money to capitalize on a lot of his ideas, but Edison did. So Edison, even though he lost out on the bid to the World's Fair, he had all of the capital and the assets to make AC electricity work on a grand scale. And Edison eventually went and, put together businesses like General Electric, and Tesla ended up dying as a pauper. So it's a really fascinating history between the two. I highly suggest you read up on it and just kind of make your own decision as to who's right, who's wrong. Science versus business, capitalism, humanitarian efforts, things like that. And so this is going to bring us to the end of this video. Another thing I'll mention about that is as Edison was carrying out the smear campaign, and as Edison executed this elephant, keep in mind that one of the patents that Edison had was for the first working motion picture camera. And Edison actually taped this execution of the elephant. And if right about now, I can see most of you going to Google and looking this up, and it is out there. It's a very old, grainy, black and white video, but it is there. You can see it. Again, it's not a happy video. Don't go and watch it if that kind of thing offends you. But it's part of history. It's part of what happened with the ongoing development of technology in our world. So we're going to have one more video with the Chapter 30 material. For that video, we're going to take the idea of these coils, aka solenoids, and we're going to start hooking them up to electric circuits with resistors and capacitors and switches and batteries, and we'll see what happens when we start including those inductor coils, which is what we're going to call them, these solenoids, aka inductor coils. We'll see what those do to our circuits, and more specifically, we'll see what they do to the math. Because for any circuit, keep in mind that you should be able to go through a circuit using Kirchhoff's law, and if we can add up all of the electric potentials associated with everything in the circuit, then we have a mathematical equation that tells us what's going to happen. So that's what we're going to look at for the next video. See you then.